Which is so we get our other formula. I remember you talking about this. It's like one of our, like our fourth cake formula.
This actually is more universal than is true. If used properly, it works whether the acceleration is constant or not.
Got it.
You can actually derive one of the cake formulas from this.
Right.
Yeah. All right, so this is 1/2 mass of A times VF squared. That is really not much better. VF squared plus. Now VF dot VI, I have no idea if they're in the same direction or not. However, notice there's nothing in the formula up here which cares about the order in which you do it. Once you get to here, you're multiplying magnitudes. Commutative property of multiplication holds. 2 times 3 is the same as 3 times 2. Order does not matter. So whatever that is, well, that's the negative of it. So we end up with 0. Minus, I heard somebody whisper it. There we go, a little bit more confident. And so now we are left with, almost at the moment of truth and revelation. So we now have 1/2 MA times VF squared minus VI squared. I want to emphasize we do not have the vectors in anymore. Once we did the dot product, the vectors disappeared. Taking that out one step further, we have 1/2 MA VFA squared minus 1/2 mass A times VI squared. This 1/2 mass times speed squared. And again, it is speed, it is not velocity. It is speed. This was special enough, they decided they had too much to write, so they decided to come up with a special letter in order to represent this 1/2 mv squared. And they decided on the letter K. Capital K. So we get K final minus K initial, or delta K. Yes, you've seen it derived here. We got the K. What does it mean? So now we bring in the words. Pardon? No, wrong K. This right here, force dot displacement. This is work. Symbol is a capital W. The reason I do not use capital W for weight is because it shows up here. This is work. This K right here, this is kinetic energy. Now, F equals ma. In the formula, F equals ma. What is F besides force? What force are we talking about in F equals ma?
Net force.
Yes. So the work in this case, if this is the net force, this is the net work, or total work. Thus, we have a relationship over here. Let's have to partially erase. That the total work done on an object, or net work, whichever way you want to go, total work done on an object is equal to the change in kinetic energy of that object. This is crucial enough that they came up with a name for this equation. I think it's misnamed, but they still have a name for it. This is the work energy theorem. Personally, to me, it's not a theorem because this equation is true because we define words to make it work. We define work and we define kinetic energy, so that is a true statement. At the heart of it is the definition of acceleration and displacement and the Newton's second law. That is the underpinning of this. questions to hear. All right, I now introduce two new terms. Conservative force and not liberal, non-conservative. There is a formal definition for what the conservative force is, but I think it does require calculus. So instead, I'm going to give you a list of all the conservative forces we have dealt with up till now. Here we go. You remember what it is? The entire list? Nah, that one's over here. Gravitational force. And that's it. That's the entire list right there. Of everything that we've done so far, that is the list. This includes the weight and the generalized equation. There is another force that we will deal with this semester, so I'll throw that, the ideal elastic force. I'll touch on it a little bit this chapter, but we go into more detail on it in probably about a month. And that pretty much covers this semester. Next semester, electric force and magnetic force are conservative, but everything else is non-conservative. Now, why differentiate? Why do you suppose a force would be called non-conservative?
Probably because its values fluctuate consistently.
It causes something else to fluctuate. What do you suppose is conserved? So why do you suppose something is called a non-conservative force?
Because it fluctuates the energy.
Yeah, or energy is not conserved. Yeah, it causes energy to change, the total energy to change. So non-conservative forces cause total energy, which is represented by a capital E here, to change. Conservative forces make sure the total energy stays the same. So I'm going to, well, given the time, I'm going to get down one more equation here, without derivation, but more just the concept. Non-conservative force causes non-conservative work. Conservative force causes non-conservative work is equal to the change in total energy. And so we'll sort of leave on that note right there. And I guess we pick up on those thoughts after the Ides of March. Just beware. Sunday before spring break, Ides of March.
Give us time for his class.
Is that
That way we can be happy for what actually happened rather than set those going.
I'm just trying to think of if the Ides of March have any significance other than the death of Caesar.
I mean,
Well, presumably, I mean, there are Ides of every month.
yes, but like, changing the face of an entire, empire's whole history.
Well,
Oh,
it's not
just
an
run
empire
out
at that point.
the test sheet and the practice test. You go over
Yeah,
practice
they
test
stopped that.
twice with
And
anyway.
I guess the lady empire for
You
10 years, 20
must
years,
see
yeah,
it
pretty much.
Tuesday. Nope, I will not be there.
So I don't know what this is.
That might help with this.